share live. My name tag? I don't exist. I'm just a tech guy. What? Yeah. Oh, is it on? Oh, okay. I'll test it really quickly. Let me just use it. I did not test it. You're right. I do need to do something. Okay. It's yeah. I think it's right. Ryan, you're running trivia? Post oh, okay. We can yeah. I'm just gonna test it right now. Test test 1 2. Test test check check 1 2. Test test 1 2. 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 Check check check. Okay, this works. Oh, I turned it fully off. I see.
It wasn't, the second one was the one for my talk.
Yeah.
It's the third one.
The other one is all the way off.
Never mind. I don't want to punch people.
One of them is very bright. One of them is all
This
the way
is
off.
very bright.
No, there's one that's brighter.
And this?
Yeah. I think.
I'm afraid to hit that. I don't remember which one's which.
I don't either.
Which one's the one that goes off? I think it's the bottom. It's the bottom. Well, I want to test it now.
I think it's the bottom.
I'll put it this way. We're going to put on the second one, which is like partially right.
Yeah.
So if it goes all the way right by accident, it's not going to like kill people as opposed to like dark to totally right. So like,
Okay. We're good.
Brian and I tested this and I just don't remember it.
No, there's like a partial lighting.
Yeah, I guess we started.
Okay.
But
So, all we have to do is turn on the handheld mic. But do you want to go into the, for like presenting? So it's like a little darker?
oh, sure. Thanks. Okay. Hello, hello. Hi. Okay, welcome everyone. So as you're all trickling in, finding your seats, we're going to start with a little bit of astronomy trivia. So get warmed up for this long night, or the next hour and a half of astronomy. So Selena is going to be leading the astro trivia.
Hello, everyone. I don't know if you were here last year, but if you are, you probably remember me. But something is different this year. This year, we've hired professional trivia writers for the trivia questions. There are John and William. I don't know if they're here in this room, but they are like professional at it. So it's going to be good, and it's going to be stellar, and you're going to be stellar at doing them. So let's start. All right, question 1. Most luminous matter in the universe is composed of hydrogen and helium. All elements heavier than hydrogen and helium are referred by astronomers as metals. Sorry, chemists. How much of the universe's luminous mass is composed of metals? A, 0.02%. You raise your hand if you think it's the answer. Okay, a few of us. Oh, more of us. B, 0.2%. Ooh, a lot more of us. C, 2%. Ooh, okay, equal amount. D, 20%. That's a lot. Ooh, okay, 1%. All right, lock in answers. It's actually C. So hydrogen accounts for hydrogen accounts for around like 75% by mass, I think, or wait, by number of the universe's luminous matters, and helium accounts for around 23%, and the rest is the metals. All right, question 2. The majority of elements on a periodic table were originally produced by stars, either during their lives or during their deaths. Which stellar process is the main producer of gold in our universe? A, the explosion of a white dwarf, a very tiny star. B, the explosion of a very massive star. Nobody? Okay, some people. C, the collision of two neutron stars, very, very tiny stars. Around like 10 kilometers in diameter. Okay, a few of us. D, the merger of two black holes. Nobody? All right, lock in your answers. It's C. So all elements up to plutonium are created in stellar processes. Most of the heavy elements like gold, platinum, and uranium are produced by merging neutron stars. So there are stars 10 kilometers in diameter, super, super dense, like sun mass, but tiny, like a Manhattan-sized sun. Question 3. At the end of the lifetime of a very massive star, so that's anything from 8 solar masses to like 30 or 50 solar masses, the star's core will collapse onto itself, producing a brilliant core collapse supernova explosion. Roughly how long does this process of core collapse take? A, 1 second. Okay, a few of us. B, a day. Even less of us, okay. C, 10 years. All right, D, 10,000 years. Oh, that's a long time. All right, lock in your answers. 3, 2, 1. So these massive stars can actually live up to 500,000 to 550 million years. So compared to their lifetime, their collapse is actually extremely, extremely short. So I wouldn't get it right if I didn't know the answer already. Kudos to the people who got it right. Question 4. When a white dwarf star becomes too massive, usually by stealing mass from a nearby companion star, explodes as a type 1a supernova. The brightest observed stellar event in recorded history, SN 1006, was the result of a type 1a supernova. Roughly how much brighter was SN 1006 than Venus? A, 2 times. All right, nobody. B, 20 times. C, 200 times. Okay, a bit more. D, 2,000 times. That's a lot of us. Okay, let's see if we got it right. 3, 2, 1. B. So SN 1006 exceeds roughly 16 times the brightness of Venus. Fun fact. All right, last question, I think. A supernova explosion, oh, never mind, this is not the last question. A supernova explosion occurs inside the Milky Way roughly once every century. The Crab Nebula, shown in the background, very pretty picture, is the remnant of one of these supernovae. Chinese astronomers observed this explosion in 1054 AD. So that's like 1,000 years ago. But how long ago did the explosion actually occur? A, 969 years ago. Nobody? B, B, 7,500 years ago. Okay, a few more of us. C, ooh, that's a huge number, 105,000 years ago. And D, that's a very long time, 2.6 million years ago. Okay, way more of us. Let's see. Lock in? Are we locked in? 3, 2, 1. So the Crab Nebula is roughly 6,500 light years away. So that's like light has to travel 6,500 years from the event to get to us. So that plus whatever the difference between now and 1054 is, that's the correct answer, which is around 7,500 years ago. All right, 3, 2, 1, last question. This is a picture question. Which of the following most closely resembles the future state of our sun immediately following its death? You can take a moment to appreciate these pretty pictures. I'm not going to tell you what they are right now, so it's fun. All right, any team A's? All right, a few. Team B, pretty colors. Team C, some spinny jetty things. All right, Team D, a butterfly thing. Ooh, wait. We have like way less participation for this question. What happened? Nobody wants a team? All right, lock in your answers. It's actually D. So choice D is the planetary nebula. Right here, it looks like a butterfly, and it's called the Butterfly Nebula. The sun will become a planetary nebula in roughly 5 billion years. So we kind of have like 5 billion years on Earth for humanity if we hold that long. Choice A is a accreting white dwarf about to become a type 1a supernova that we just mentioned in the last problems. Choice B is a remnant of a type 2 supernova. And choice C shows 2 merging neutron stars, the stars that are sun's mass but tiny in diameter. So hopefully that was fun. Thank you again for John and William to write the questions, and thank you for Ryan for hosting, and Alex, I don't know if Alex is in this room, and every volunteers. And we are now ready for Jenny's talk. I don't know, Ryan, if you want to say more. Okay, perfect. Ryan's going to introduce Jenny.
Okay. Hi, everyone. My name is Ryan. I'm a PhD candidate in the Columbia University Astronomy Department. And for the past year or so, I've been coordinating and organizing Columbia Astronomy's outreach initiatives, including these Friday public lecture nights. But before I say anything else, I do want to emphasize that the organization of these events is not a single person thing. We've had a ton of help with this. So I want to first thank a bunch of people. First, Alex Masagian, who I think is still upstairs on the 5th floor. Justin Vega, who is a foot away from me. Chris Carr, James Sullivan, who is providing us with hot chocolate for later tonight. Michael Masser, who's also helping with hot chocolate, and who all helped a lot in organizing and putting this event together. I also want to shout out Selena Yang for running the trivia. You just saw her. And thank you to William and John Kroger, who wrote the trivia. Also, thank you to all the other volunteers who helped set up this event. And of course, thank you to all of you for coming out tonight. So a huge round of applause to everyone. Thank you all so much for coming. Cool. And so this is our first outreach event of the 2023-2024 academic year. So I just want to quickly take a poll. How many of you are brand new to our public lecture nights? Raise your hands. Cool. How many of you attended at least one event this past year, like spring 2023 or fall 2022? Nice. How many of you had attended any events prior to 2022? Nice. Okay, so we have a fantastic mix of returning faces and new faces, which is great. So especially for the newer people, I do want to give like a very quick, just a few minutes of overview of what you can expect from these public lecture nights, what we're currently working on to expand these public events, and broadly, what our goals are for this public outreach for 2023 and 2024. So yeah, we try to hold these events every other Friday, roughly. We started a bit early this semester. Sorry, not early. We started a bit late this semester. So we're only holding 2 events this semester, one tonight. We also have one planned for December 1st in 2 weeks. But we will be back in 2024, hopefully mid to late January, with a whole slate of 5 to 6 events to last us all the way through the spring semester. So that should be very exciting. And these events are free. They're open to anyone. We try to make them child-friendly. We try to make them accessible and fun for anyone, regardless of science or astronomy backgrounds. So in the future, you can bring your friends, bring your kids, bring your work colleagues, bring your arch nemesis, anyone you want. They're all welcome here. So for the next few months, we're trying to make these events a bit more robust. We're going to try to mix in a few more different activities, like trivia and maybe some like astro current events, maybe some panel discussions with Columbia astronomers. That should all be very exciting. And this will especially be useful for days where we can't go outside to stargaze or use the telescopes. Like tonight, unfortunately, it's a bit too cloudy for us to actually see any stars. So instead of stargazing tonight, we'll be having a reception after the talk where you can all feel free to get hot chocolate or tea and talk to any of us. I apologize for not being able to stargaze tonight, despite my best efforts. The National Weather Service refused all my requests to blow the clouds from New York into New Jersey. I'm disappointed, to say the least. But we will be making it up to you. We'll be scheduling a number of independent public observing events, either on campus or elsewhere in the Upper West Side or elsewhere in Harlem throughout this academic year. So we'll try to do observing during our lecture nights, if it's clear. But other than that, we'll be doing more observing on other days. Also, this year we are aiming to do a bit more outreach to high school classrooms and to public libraries in the area. So if you are a local high school teacher, or you're a local librarian, or you know a librarian, or you've been to a library, or you've read a book, then definitely come see us afterwards. We'd love to talk, we'd love to connect, and work together over the next few months. So, as I said, tonight, so we do the trivia, then we're going to hear from Jennifer Mead, who's going to give a wonderful talk on Tales from the Stellar Graveyard, the Ghosts of Stars Past. Then we're going to have a short Q&A with Jennifer, and then we're going to have a reception where any of you can ask questions. And if you want to keep up with our any of our outreach activities throughout the year, we have mailing lists or an email list. So if you go to tinyurl.com/astrosignin or scan the QR code, you can sign up for the email list. You can also email us at astro.outreach@gmail.com, or you can talk to any of us with name tags afterwards. So, okay, I've talked enough, but now I want to introduce our speaker, Jennifer Mead. I am incredibly excited to introduce Jennifer, my friend, my office mate, a fantastic scientist. So, yeah, when you ask most people what their favorite fantasy setting is, people might say Middle-earth, or Hogwarts, or Tatooine. When you ask Jennifer what her favorite fantasy setting is, it's definitely Central New Jersey, where she was born and raised. Some people may doubt that Central New Jersey is a thing, but she is flesh and blood proof that Central New Jersey exists. And she went to Rutgers University in New Brunswick, also in Central New Jersey, where she got degrees in, well, she got a Bachelor's of Science in economics, mathematics, and astrophysics. So she's a perfect candidate to run our future interstellar economy. But now she's a fourth-year PhD candidate in the Columbia Astronomy Department. She's also an NSF Graduate Research Fellow. And her research involves studying and trying to understand how the very first stars in existence came into being, and how these very, very first stars from billions of years ago have influenced all the further generations of stars and galaxies from hundreds of billions, no, not hundreds of billions, a few billion years ago to the present day. And she'll be talking a little bit about that today, or how the past generation of stars can influence the future generation of stars. So when Jen isn't doing research on stars or galaxies, you can probably find her singing karaoke in her room or elsewhere, or you can find her tending to her incredibly impressive garden at her home in the Garden State. You can ask her any questions about her garden. It is quite something. And one more thing before I let Jennifer speak. A little bit of a warning, maybe, or like caution. So Jen is a third-degree black belt in karate. This is not a joke. She's a third-degree black belt in American Ishinryu karate. So I'm sure all of your questions will be fantastic tonight, but just like, I don't know, exercise some discretion. And if you do want to ask any anonymous questions to Jen or any of us anytime tonight, you can go to tinyurl.com/astro-questions-NOV17 for November 17th. It's a Google form. You can submit your questions as Jen is speaking, or once we do the Q&A afterwards, and all the questions will pop up here. So, okay, without any further ado, I'm super happy to welcome Jen, who will be talking to us about the Ghosts of Stars Past. Oh, yes.
Thank you, Ryan. Okay. Okay, thank you, Ryan. Now that my mic is working, in theory, we are going to now bring up my talk. Uh-oh, something's doing something. Is that just the error? Is that feedback? Oh, we're not duplicating it.
That's something else.
All right, I'm 95% sure no, that sounds like feedback. Maybe that's not feedback. It's just a delay. I muted. Test, test. Oh dear. My Zoom is muted. I swear we tested this before. Test. Hello? Oh, we're still echoing. What if? No, I guess we need the mic for the live stream. I was going to say I could shout at all of you. I'm very loud. Yeah, I could use the handheld. Let's do that. Hello? Are we echoing less now? A little bit less. Okay. I'm going to get started, if that's okay. All right. Thank you, everyone, so much for coming to our very first outreach of the semester. I am very honored that Ryan let me speak first to all of you. So today I'm going to tell you a very spooky story about the ghosts of stars past. All right, let's get started. Let's set the scene. So somewhere out in the vastness of space, about, I don't know, 10 million years ago, a star and all of his little star buddies were born from a cloud of gas and dust. But in a story that is unfortunately tragic and very familiar to many stars, it ends with a bang. So our poor little star, just the one in the center, has turned into a ghost of a star. And of course, all of his little star friends are appropriately horrified. But they want to know what happened to their friend, right? They want to figure it out so it doesn't happen to them. Spoiler alert, they can't avoid it, but that's just too bad. So,
Self-destruct sequence.
I'm spoiling it here. All right, let's start off with the number of ways that stars can die. So first up, we have our core collapse supernovae, which are essentially the self-destructive
Sequence
stars.
has been initiated. Warp core overload in 1 minute.
So if you're a Star Trek fan, you got that. If you're not a Star Trek fan, you need to fix that. But core collapse supernovae are the self-destruct sequences of stars because nothing triggers it except the star itself, okay? So this happens for really massive stars that are more than 8 times the mass of our sun. So those are some pretty big stars. And essentially what happens, so some of you might know that stars do nuclear fusion in their cores. Now what is nuclear fusion for those of you who don't know? It's basically when we take atoms and we smash them together and we build bigger atoms, right? But this process is only good for so long, right? We can only build so many elements with that because at some point we stop putting out energy and it starts to take energy to force all of those atoms together. And when we lose that energy, right, there's no longer pressure, there's no longer energy that are holding up the outer layers of a star. And so the outer layers of a star begin to collapse inward and they bounce off the core of the star and explode outward in a very violent explosion. So as you can imagine, that's going to spread the guts of stars pretty much everywhere across the universe. Are we good? We're not on the PowerPoint. I am clicking. We're not on the PowerPoint. Are we sharing? Can we share it again? Just click here. Here we go. There we go. Okay, sorry for the technical issues, guys. So, our second option for stars dying / spreading their guts all over the universe are white dwarf supernovae. So we talked a little bit about it in trivia. These are the type 1a supernovae. And this is essentially, you can think of it as the cannibalism of another star. Stars are like really weird, okay? This essentially happens when you have a white dwarf, which I'll get to how you get one in a second, but you have a white dwarf and it has a friend, although you might not think it's a friend after I tell you what it's about to do, because this white dwarf is very hungry and its friend got a little bit too close. And so that white dwarf is going to start to eat the outer layers of its supposed friend, right? Now, many of you know that if you eat too much, you're not going to feel so great and you might puke your guts up, right? And this is exactly what happens with this white dwarf. It eats a little bit too much of its friend, and guess what? It doesn't feel so good, and it explodes all of its guts all over the universe. Delicious. All right. 3, we have mergers. So I'm going to specify that these are neutron star mergers. You can have mergers with neutron stars and black holes and black holes, right? Any number of things. But I care about neutron star mergers, which you'll see in a little bit why. And you can think of these as the stellar car crashes of the cosmos. And so if you're from New Jersey, like I am, you know that circles are very dangerous, and going in a circle is very dangerous. And so it may not surprise you that things that are going around in circles may crash. And this is exactly what happens. So if you have 2 neutron stars, or really 2 anything that are orbiting each other, their orbits will eventually in-spiral. They'll get closer and closer together until they crash and merge. Again, really big boom, lots of guts everywhere. Lastly, we have what are called planetary nebulae. So this happens for stars that are less than 8 times the mass of the sun. So this is what's going to happen to our own sun. And you can think of this as an extreme weight loss routine. Oh, too far. Extreme weight loss routine for stars. And so what happens at the end of a smaller star's life is that it begins to eject the outer layers of the star itself. It's a little bit less violent, right? But it's actually very beautiful. And so what you get left with is actually a white dwarf, which is just the core of a star. And so this is how we get our white dwarfs for those white dwarf supernovae. You only get a white dwarf supernovae, though, if it has a binary companion. So there's a second star in the vicinity. All right. So we talked about 2 very violent explosions being supernovae. So just like a quick raise of hands, how many think a supernova is similar to a nuclear bomb going off? Just like a quick show of hands. Okay, that's not many, and that's good because it's not. It's actually 10 to the 30, so that's 1 followed by 30 zeros, and I still don't know what that means. That's 1 trillion million, which I still can't picture, but it's 1 trillion million nuclear bombs going off. That's a lot. Now, this is where I may or may not get in trouble with the FBI for doing this research, but I decided it would be fun to think about how many nuclear bombs we could fit inside the Earth, just to kind of get it, because like, I don't know what 1 trillion million means, right? So I said, okay, like, let's think about how many Earths that would be, right, if we were to try to like stuff them with nuclear bombs. So 1 nuclear bomb is approximately 10 feet by 5 feet by 5 feet. So like my height by 2 times my height. All right, so can I get any guesses for like if we were to just hollow out the Earth and stuff it with nuclear bombs, like how many Earths we would need to fit 10 to the 30? Just shout it out. 300. A trillion. Okay. Any other guesses? 100 trillion. Okay. Those are pretty big numbers, and that's actually good. I'm glad you guessed big numbers. It's a big number. It's only 5 billion. Only 5 billion. But you need like 5 billion Earths to fit 10 to the 30 nuclear bombs, which is like a lot. I still don't know what 5 billion really means, so I put that in terms of suns for you. That's like 5,000 suns, which is a lot. So as you can imagine, if you are setting off a nuclear bomb that essentially takes up the volume of 5,000 suns, that's a big boom. And so it may not surprise you that stars smear their guts all over the universe when they do that. And so I just wanted to quickly show you a couple of pretty animations of what that looks like. So this is a planetary nebula. This is what would happen to the Earth, or not the Earth. The Earth is going to get swept up in this, but this is what's going to happen to the sun. This here, when the GIF restarts, there we go, is a merging neutron star. And we also have an example of a white dwarf supernova. And so these explosions are so incredibly large that the typical size, by about 200 years after the explosion went off, is about 10 light years. That's more than 2 times the distance to our nearest star. So these are really, really big. And I don't remember if Ryan mentioned this, but I simulate things. So I do a lot of computer stuff. So I'd be remiss if I didn't mention that we can also simulate this. And so this is just a really quick video from the Renaissance simulations. I do not work on it, but some of my collaborators do. This simulates the first 400 million years after the Big Bang, and it occurs to me that I'm going to turn off the lights very quickly. I'm going to pray that's the off button. All right. There we go. So what you're actually seeing, those little balls of gas, are actually stars being born and heating up the gas around it, not supernovae. But as you see right here, that is a supernova. And you can see it go well beyond the confines of its galaxy, right? And there will be another one going off in the top right in a second. There it goes. So again, we are able to simulate the fact, and lights are coming on, so watch your eyes. We are able to simulate the fact that stars blow their guts all over the place. And it's quite beautiful, if you ask me. Now, I forgot that was there. Now, I liken this, though, to a witch's brew because these guts go everywhere. And so galaxies and the stars that form from the dust and gas are sitting in a witch's brew of elements, right? It's just like this soup, right? And so, I bring up the periodic table because almost every element in our universe is actually formed in stars, with the exception of some of the ones along the bottom here, which are man-made. Now, I'm going to take a step back for a second for some of the younger audience members and those of you who may not be as science-minded, and just back up and what is an atom, right? Because what an atom is, how we get elements, is actually very dependent on how these things are structured. And so atoms, and many of you I'm sure know this, but I'm going to go through it anyways, are made up of protons, neutrons, and electrons. Now, the nucleus of our atom, so this is the center of our atom, are made up of protons and neutrons, right? And then we have an electron that's just kind of like whizzing around on the outskirts, right? So this very first atom is hydrogen, right? It's just vanilla hydrogen, just a basic proton, neutron, and electron. That's the very first element on the periodic table. Now, we can add a proton, neutron, and an electron, and then it becomes a new element. It becomes helium. That's the second element on our periodic table. And we can keep going like this. If we add another set, it's lithium. And in yet another set, it's beryllium. Now, an atom, right, is any combination of these, protons, neutrons, and electrons, right, kind of in a single thing. But many of you, and so for, again, the younger folks in the room, right, you know what an element is, right? You breathe oxygen. Oxygen's an element, right? You are made of carbon and hydrogen, also elements. You drink water, that's a molecule because it's many atoms, right? Hydrogen and oxygen combined. Now, I'm going to switch terminology a little bit. I've been talking about what's an atom. I do want to talk about what is an element, because elements are basically just which atom are we looking at. So what's important, though, about an element is that you can take away neutrons, right? And it's still the same element. Let's put those back. You can add in neutrons. It's still the same element. Let's take those away. You can even take away your electrons and still have the same element, okay? So there are different configurations of the atom that still leave you with the same element. Let's put those back. So what's really important here is that an element depends on the number of protons that you have. And I'm going to emphasize that because it's going to be important in a couple of slides. All right, so let's go back to our periodic table. So let's go through what was produced where. So our first two elements, hydrogen and helium, were formed in the Big Bang. So as Selena mentioned during trivia, 75% of our universe started off as hydrogen and 25% as helium, right? We had like a little bit of lithium, but really nothing that's like worth mentioning. And our universe is still pretty much 75% hydrogen and 25% helium. We have a little bit more of what astronomers call metals, which is like literally everything that is whited out on this periodic table. Like everything is called a metal except hydrogen and helium, just so you know. That is the astronomer's periodic table. All right, so I do actually want to mention that this is the place in my talk where I stuck all of my really terrible jokes, so I'd appreciate it if you laughed somewhat like that. Hee hee hee. Okay, thank you. All right, moving on. So next we have our core collapse elements. So these are elements that are produced by our dying high mass stars, that self-destruct sequence of stars. And so these are what are called alpha elements, so named because we get them by smashing alpha particles together or onto other atoms. Now, what's an alpha particle? It's super simple. It is just the core, the nucleus of a hydrogen atom, so 2 protons and 2 neutrons, right? Just keep tacking them on, right? And you can get all of like these lighter elements by doing that. So I guess one thing I do want to ask, and this is another terrible joke, and I'm going to point it out right now. What do stars say to their friends that are like about to go supernova? Any guesses? We'll miss you when you are gone. It's terrible, I know. All right, moving on. I'll give you a break from the jokes for a second. Next, we have our white dwarf supernovae. So this is the cannibalism that I talked about. This produces what are called the iron peak elements, so named because they are around iron on the periodic table. Astronomers are so creative. We also then have our merging neutron stars. So this is where the idea of neutrons kind of comes into play. Unsurprisingly, if you smash a bunch of two stars together that are made entirely of neutrons, you're going to have a lot of neutrons flying around. I think that comes to no one's surprise. But the importance of this is actually that all those neutrons that are flying around get tacked on to other elements, right? So remember how I said that you could, add neutrons onto an element, right? It doesn't change the element, but you can add neutrons onto it. Now, you might say, okay, but then how do you get any of these elements on the periodic table, right, if you're just tacking on neutrons? And it's actually through a process called beta decay. And so what happens is that your neutron ends up turning into a proton and an electron. And if you remember what I said, if you change the number of protons, then you could change your element. So this is what's called the rapid neutron capture process, or our process, because we are rapidly capturing neutrons. And so we're very rapidly able to move up the periodic table through this beta decay process. We get a lot of protons very fast. All right, and then lastly, we have our dying low mass stars, so these are planetary nebulae, and this produces a set of elements known as the slow neutron capture, or S process elements. Perhaps you can figure it out, but this is because we are slowly capturing neutrons. So it's the same process where we beta decay and we build up elements on the periodic table, but we get some of those lighter ones because we don't go so fast. Now, we have all of these like dead stars lying around, and you might ask, what do we do with them? You bury them. All right, I have like a whole host of like other periodic table jokes, but nah. All right, no, for real though, I'll move on. So I do want to show you guys some what I think are very beautiful pictures of supernovae. So they're all supernovae here except for the one down here. This is the Ring Nebula. It is actually a planetary nebula. But I want to show you these because they're actually chock full of information for astronomers. And so I want you to focus at the one on the bottom right, because I'm going to switch the image here. What you're seeing here is an image that is colored by the element that gas that we're looking at is made up of. And you might say, okay, Jen, like, you're pulling some magic here. How do you know exactly what element like all of this gas is made up of and exactly where? And this is actually because every element on the periodic table has a unique set of color fingerprints, just like you and I have a unique fingerprint on our fingers. But elements each give off their own unique set of colors. And so astronomers detect this through a process called spectroscopy. Essentially what we do is we take light through our telescope, and then we are able to break it up into its component colors, which you'll get a chance to kind of do in a couple of minutes. And so what I'm showing you here is what's called a spectrum. Essentially what it is that on this vertical axis here, we have the brightness or the amount of light that we get for different types of light. So this is technically wavelength, but you can think of it as different types of light. So this thing kind of on the left here, this is the visible spectrum. This is what you and I can see, right? This is Roy G. Biv. But there's also other types of light that we can't see, right? There's the ultraviolet light, so this is the kind of light that burns you when you're out in the sun. There's also infrared light, so if you've ever looked through a heat camera, right? Humans show up pretty brightly on a heat camera. That is because we give off infrared light. And so we have, each of these, every object, right, peaks in a certain type of light. The sun, maybe unsurprisingly, peaks in the visible spectrum, right? This is what we can see. This is clearly our sun. Us as humans, we peak in the infrared here. So this is about 98 degrees Fahrenheit. So everything emits light in some form, whether you can see it or not. And this is like cool and all, but you might say, okay, I don't really see how you're getting information about elements from this, and that's because we are too zoomed out. So if we zoom in a little bit, you'll actually see that these spectra are full of like little deviations, these little points where the brightness is actually higher at certain wavelengths than others. And these points where the brightness goes up are exactly the fingerprints of various different elements. And as I said, each element has its own unique fingerprint. So each of these lines, right, corresponds to a unique element. All right, so this is where the fun part comes in. If you have not already gotten a diffraction grating, that little piece of plastic when you walked in, I'm actually not sure where the boxes are. I don't know if they're actually at the front of the room. No, they're not, but okay, there's a box here and a box in the back. If you do not have one, please go get one. You guys should, I mean, it's fine, but you've seen it. All right, so diffraction gratings are super, super cool because they're a really basic version of a prism, right? Pink Floyd drew an awesome version, like, representation of a prism on their Dark Side of the Moon cover. But essentially what your diffraction grating does is it takes light that is incident or coming into that piece of plastic and it breaks it up into its component colors. All right, I'm going to turn off the lights in the room. So if you are not, I'm going to wait for everyone to grab a seat before I do that. I think it's this bottom one. All right, is everyone settled? Can I turn off the light? All right, we're turning off the lights. Okay. So what I'm going to do is I'm going to turn on a series of lamps. And each of these bulbs contains a bulb. Sorry, the bulb contains a bulb, yes. The bulb contains gas of a specific element. And so what I want you to do is I want you to hold your diffraction grating, your piece of plastic, up close to your eye, and just think about what you're seeing, all right? So this first one is hydrogen. This is the most basic element that we have, right? One proton, one neutron, one electron. It makes up 75% of our universe. And so you should be able to see two very distinct lines. What colors are they? Red and like a cyan bluish color, right? So hydrogen in the visible spectrum, in the Roy G. Biv, right, has two very visible lines. Now our telescopes, of course, can go beyond this, right? We can see in the UV, we can see in the infrared, right? We can see in the radio, the microwave, you know, so forth, X-rays, gamma rays, right? And hydrogen gives off lines in many of those different wavelengths, but of course the only ones we can see are in the visible. All right, I'm gonna turn this one off. This next one is helium. So this is the second element in the periodic table. And we see a couple more colors, right? But still some very distinct lines. But these lines are different from the ones in hydrogen, right? It's a slightly different red, right? We've got a couple more colors. All right, has everyone gotten their fill of helium? I'm going to turn that one off. All right, this next one is mercury. It's a little bit fainter, right? Again, a different fingerprint than hydrogen and helium. All right, I'm going to turn this one off. Next we have argon. This is, you know, again, stars will miss you when you are gone. Another faint one, but again, distinctly different. All right, I'm going to flip this one off. We've got two more. This one on the end here is nitrogen. All right, I'm going to flip this one off, and we're going to come back to the other end. We've got one more. This one is neon. All right, has everyone gotten their fill of beautiful neon? All right, I'm going to shut this one off. All right, the lights are going to come back on, so you have been warned. Hopefully not too bright. All right, so your diffraction gratings are, let me tell you, super fun. This was my favorite thing to play with when I was taking my intro physics classes. They handed out one of these, and I took it home and I looked at like everything. You should not look at the sun with these, but you can put it in front of the sun and try to like see it out of the corner of your eye, okay? All right, so I want to return to, and you know, wrap up by returning to this image of our supernovae. So what I'm showing you in the center is Cassiopeia A, that's the one that's on the bottom right, in the optical. So this is just all of the colors in the visible spectrum kind of thrown together. Now that you understand that every element has a different fingerprint, right, we can take those elements and we can kind of like piece them together like puzzle pieces to make up, all of the lines that we see in a spectrum. And that's exactly what astronomers do. So we are able to see things like oxygen, which is in purple. We can see things like iron. We have silicon and magnesium and titanium. And so for those of you who are like really paying attention to the periodic table, you might remember that these are all alpha elements. These are all elements that are produced in our core collapse supernovae. And so this was and you can look it up on Wikipedia because I did, this was a very massive star that went off, self-destructed as a core collapse supernova because of the elements that we see in it. All right, so I want to leave you guys with a little bit of hope that actually, so I've talked a lot about death, and stellar death in particular, but there is hope. There is, in fact, life after death, because all of those elements, all of those star guts that have gone out into the universe get mixed into clouds of gas and dust that then cool and form new stars. This is where our sun came from, this is where we came from, and this is our fate as well. So what you're looking at here is an image from the James Webb Space Telescope's mid-infrared imager. I'm giving away the ending here, but this is a picture of the pillars of creation, so named because in these little circles here, you can see new stars forming. And you know these are new stars because this is actually again, an infrared imager, so we're able to see through the clouds of dust and gas in this wavelength. And these stars are forming at the tips of these pillars of creation, or it appears that they are, because they are blowing away the gas and dust around them with their stellar wind. And so there are, in fact, new stars forming from the guts of old stars. And so, as famous astronomer Carl Sagan once said, we are made of star guts. Thank you.
Fantastic talk. Give another round of applause for Jen. And yeah, now we'll do maybe 15 minutes of Q&A. Again, you can submit questions anonymously on tinyurl.com/astroquestions-note17, or we'll have people running mics if you want to ask questions in person. And yeah, I do want to reassure everyone that the technical issues we've been having were completely intentional. Part of the process of doing outreach is showing the process of doing science, and we have problems with technology every day. So this is all perfectly planned. But yeah, does anybody have any questions for Jen? I think as we're running a mic up there, we do have a question on here. So that question is, why are planetary nebulae called that when they don't have anything to do with planets? Crying face emoji.
Pretty sure that's historical because astronomers love sticking with historical stuff. I could give you so many instances where astronomers are doing something kind of insane just because we did it in the past. Yeah, no, planetary nebulae, I'm pretty sure are called that just because that's what we thought they were in the beginning, right? They're actually about they're closer. They're much smaller than supernovae remnants, and so they're closer, though not quite the size of solar systems, right? They are bigger, but so I suspect that's why they're called planetary nebulae, just because astronomers can't let go of history.
Also, we're going to transfer to the podium mic so we can run
yeah.
the.
There you were. No, that one. will now stand here. Okay.
Okay, there's a question for the.
Who had the question? Raise your hand again, please. Awesome, thank you.
Hello. So, what exactly are the diffraction gratings made out of? Is it like just some special plastic, or is there some other process that goes into making them?
Yeah, it's quite literally plastic, but something special is done to it, which is that they cut thousands. I believe the particular diffraction grating that you're holding is like 13,500 slits per inch. So they cut these little tiny slits into that piece of plastic, these really tiny slits, because what it does, and I'm not gonna, unless you want me to, I'm not gonna get into the physics of this, you can look up these single and double slit experiments if you're curious. But essentially what happens is that when light passes through an opening that is approximately the same size as the wavelength of that light, it ends up like diffracting outward. And if you only have a single slit, right, it's going to just be like one kind of wave that comes out of that. But if you have many slits next to each other, so this is the double slit experiment, that's really the one you want, these waves end up interfering with each other. And so where the waves overlap, right, where you get like two peaks in your wave, right, you get constructive interference, or two troughs, you get constructive interference, so you get bright spots. And then where you get like a peak and a trough in your wave, they destructively interfere, and so you get nothing, right? And so this is exactly what's happening in that piece of plastic, right, is that you have waves that are going through from this side, right, from my side, over here, into your plastic, and then they're interfering with each other, leaving you with different points that are bright, different points that are not bright. Now you might ask, okay, so that's great and all, but like, how does it, break up the different component colors? Well, that's simple, which is that every wavelength of light bends slightly more or less than other wavelengths of light. All right, so, red light will bend the most, and purple light will bend the least, all right? And so you'll end up with, that's how you end up with a rainbow.
Okay, maybe another question on here.
Yeah.
Here's a tough one. Actually, maybe that's.
If you were to hold one of these up to like the sun, what would it look like?
It would look like a rainbow, pretty much. So what I, all right. So what I showed you are what are called emission spectra, because they are emitting light, right? They're emitting specific wavelengths of light. The sun has what is called an absorption spectrum. So the sun emits in like every wavelength of light, okay? So it actually has what we call an absorption spectrum, because the molecules and the atoms in the atmosphere of the sun actually just, they absorb in the same way that they emit, right? And so what you'll actually see is a rainbow with some dark spots. And those dark spots are exactly the molecules, the atoms, right? It's the exact same, so if there was hydrogen, which there is, right, in the sun, instead of seeing a bright spot of red and blue, you would see a dark spot of the same red and the same blue.
Hi, Jen. Thank you for giving the talk. I had a question about the periodic table you showed with all the different ways those elements were created. I saw that a lot of the heavier elements were created by the merging of two neutron stars, and I was wondering how those elements were created if the neutron stars don't actually have any protons or electrons to create them with. Thank you.
This entirely depends on there being other elements around, right? So your neutron stars are entirely neutrons because of degeneracy, and if you want to look into this, this is like quantum mechanics. If you're interested, you can do that. But yeah, this entirely depends on there being essentially other nuclei around, right? And there is plenty out in the universe, right? Even works just starting from like hydrogen, right? And you just need like a starter thing just to tack on a neutron. That's it. Mm-hmm.
So I'm just curious, what might be after one of these booms, right, and the guts go everywhere, what's the time frame of the organization of elements after that, right? Because everything scatters, everything breaks its orbits, right, element-wise. Is there an estimate of how much stuff, how many protons there are floating around out there that are not included in an atom, or neutrons or anything like that?
There are a lot.
I would suspect there's a lot, right?
Yeah.
Okay. I must have
Lots of just like protons flying around.
So in the element range, I mean, what percentage is the guess of what's actually organized in atoms as opposed to unorganized?
Oh, that's a good question.
I mean, is it
I feel like I should have
2%,
learned this already.
less than 1%, or is it
No, it's a solid fraction, right? Because I guess here's the thing, right? Because even just a single proton is still hydrogen, right? It is a positive ion, right, of hydrogen, but it's still hydrogen. So, do you mean things like heavier than hydrogen, or? Yeah, so most of what's out in the universe, right, is either neutral, what's called neutral hydrogen, right? It's a proton and an electron, or literally just protons flying around, but that's still hydrogen. Yeah.
Actually, yeah, maybe another question here. This is a tough one. What is your favorite type of supernova and why?
Oh. I think right now my favorite type of supernova is a core collapse supernova, but that's just because in the science that I do, the alpha elements are easier to see in the spectra, and I like that I'm able to see them. It makes my science easier.
Hi.
Hi.
So I noticed you said that most of your work today, and I think for many of the scientists here, involve a lot of modeling on your computer, which I know it's really cool and going to advance the science a lot. It's just like not in my image of, the good romantic old days where you have this giant telescope, which we do have upstairs. And I used to go to Cornell, and we had also a giant telescope. And on the special days, they'll let us not actually touch it, but look through it. Do you do any of that here anymore with the outreach programs? Does that telescope do any actual research anymore? Just curious to know.
Yeah, that's an excellent question. So like you said, most astronomers actually just sit behind a computer. I don't want to romanticize it because it's actually fairly boring. If you just want to if you want to watch an astronomer, it's literally, it could be any other desk job, quite frankly. What I think makes it special is that we're doing astronomy, right? Which I think, and maybe I'm biased, but I think it's cool. With respect to the telescope, not a lot of astronomers work at telescopes now. A lot of us do work with data that comes from telescopes. But a lot of people are not sitting there taking data. With respect to the telescope that is on our roof, yes, in theory, we do use it for outreach. I say in theory because we're not actually able to get up there right now. But, you all should impress upon Columbia that they need to fix the stairwell so that we can get to the roof. And if we put enough pressure on them, we will be able to get up to the roof and use that telescope. That telescope is used, it's mostly a teaching telescope now, so we use it in our labs. But we do use it occasionally for outreach. When we're able to get up there, we're hoping that we'll be able to hook up a camera so that, there's a lot of you guys here and that dome is pretty small. But we'll be able to hook up a camera to it and, look at images through that telescope, maybe just not from the dome itself. We can have smaller groups go up. That telescope is actually fairly small in terms of telescope sizes. I think it's like a half meter. No, not even. 18. I don't even know. It's no bigger than a half a meter. Some of the biggest telescopes in the world that exist right now are 10 meters in diameter, which is very large. So those are that's like the Keck telescope in Hawaii. We are currently working on building much larger telescopes. So the 30-meter class telescopes, the Giant Magellan telescope, the 30-meter, creatively named 30-meter telescope, are both projects that are kind of in the works from the ground. So we are going to be getting like way cooler data.
Hi, my question is, considering that the universe is expanding, will this process ever stop at some point of creation of new stars and everything goes dark? And when will it be?
I can't tell you when, but I would actually say, yeah, probably, because, so here's the thing. Gravity is, so the expansion of the universe will take over on the largest scales, right? So we're able to look out and see hundreds of billions to trillions of galaxies, right? But one day, very far in the future, I promise none of you need to worry about this, all of those galaxies will eventually, be expanded, not expanded, that's not the right word. The space-time, right, between us and those galaxies will expand so that those galaxies are now beyond what's known as like the horizon, right? The light from those galaxies that are emitted will not be able to travel in order to reach us. So we will be alone, the Milky Way will be alone, or I guess the Milky Way Andromeda, because that's gonna happen first, right? But whatever this galaxy is, will be alone, right? And yes, at some point, star formation is going to stop because we're gonna run out of gas, right? So you need gas to form stars, and eventually, all of that gas is going to be used up, right? We will either have blown that gas like really far away and then like goodbye, right? Or it's going to be locked up in stars. So yeah, eventually star formation will stop.
And another question from not here. So what can the different elements in the stars tell us about the stars, and do special stars make special elements?
Oh, special stars. Yeah, so what I showed, I can't walk away from this. What I showed you today was elements that are left over from the deaths of stars, right? These are elements that have gotten mixed into the surrounding gas, right? But yeah, we can look at stars and do exactly the same thing. We get spectra. So I mentioned earlier that the sun will give you an absorption spectrum, right, as opposed to an emission spectrum. So we can look at stars and we get just a bunch of absorption spectra, and yeah, we can get, all of the elements that essentially make up that star. What these spectra can tell us is I don't want to use that word, the amount of element, right, of each element that is in a star, right? So we have some idea of how much, magnesium there is relative to the sun. We measure everything relative to the sun because that's the only thing that we are able to measure super well. We can do that for every element, right? One of the kind of long-term hopes of galactic archaeology, so this is like the idea of being able to look at the stars in our Milky Way and kind of, figure out what the history of our galaxy is. One of the long-term hopes is that we can look at a star, we can see its spectrum, and then we can figure out exactly, what kinds of supernovae went into like putting that star together, the elements in that star together. That is not something that we're able to do right now, but it's something that I'm very interested in. I know a lot of other astronomers are interested in, and just essentially being able to pull apart the history of our Milky Way.
Yeah, one more question.
What we learned today, when was it first discovered? How long have we known about it, about supernova? And how do we know it's true?
Yeah, so I actually couldn't tell you how long we've known about this. We have certainly known about the properties of light since, I believe, Sir Kelvin? couple hundred years, right? I have no idea when he was alive. It was probably actually sooner than I think. But in terms of how we know it's true, I mean, so astronomers do, we think, astronomers look at the sky, right? There's not much that we can bring down to Earth, but there are actually lab experiments that we're able to do, right? And so this is an example of one of them, right? We're able to take any element and say, okay, we know what it's supposed to look like in the lab, right? We know that hydrogen emits red and blue at these it's very specific wavelength, right? Down to like the tenths of a decimal point in, measuring like 1 to the minus 10 meters, right? And so we know the wavelengths that these elements emit at very precisely based on lab experiments. And so we are able to take that and we see that stars emit these exact same, lines, right? We're able to, it's quite literally a puzzle piece where you can take the spectrum, you could paint that on a piece of paper, you could take that spectrum, and you could just literally line it up with, a star spectrum and say, okay, those two exactly match up, and then, the helium lines exactly match up. And so that's actually like an exercise that sometimes we do. Not as astronomers, but like to teach this, right? It's like you can literally fit them together like puzzle pieces. And so I hope that answers your question.
Cool. Okay, so we're going to end the organized Q&A, but if you have more questions, definitely feel free to come and ask Jen. A few of us are going to stick around in 301. There is hot chocolate and tea set up in the 5th floor lobby for you to socialize while drinking hot chocolate and tea. So if you're a Columbia astronomer, can you raise your hands? Okay. Yeah, so feel free to ask any questions to all the Columbia astronomers should have name tags. Feel free to mingle with them. The ones with the green name tags are happy to answer any astronomy questions you might have. Jen is also happy to answer questions you might have. And so, yeah, just I guess a few more announcements before we break. One, again, if you want to be notified of any future astronomy events or astronomy outreach events, fill out the sign-in form that tinyurl.com/astro-sign-in. We will be announcing some public observing nights coming up. And so there's a great question about the dome. The dome is working, the telescope is working. There's just water damage that prevents us from getting to the roof to use the telescope. But that will be resolved by January. So, hopefully, yeah. So we will be doing lots of observing events with our portable telescopes, so on College Walk, elsewhere in the Upper West Side. As soon as we get the dome accessible again, we'll start having public observing nights up on the roof. And again, if you have any other questions, email astronaut.outreach@gmail.com. And we'd love your feedback on how tonight went, how you think we can improve things. And you can fill out feedback at tinyurl.com/astro-feedback. So let's have one more round of applause for Jen. And we'll hopefully see a lot of you in 2 weeks on December 1st, when we have another of these Friday public lecture nights. Thank you so much.
Thank you, Ryan. It's the astronomer you ask, right? We're all interested in different things, right? Offering most of the things. I'm going to go with offering most of the things. First,